Hello, this is the fourth video of a fifth vector series on lines and planes for OCR Pure Core Further Mathematics. Finding the perpendicular distance between two parallel lines. If we want to find the shortest distance between two lines in 3 dimensions, this again will be a perpendicular distance. To find the shortest distance between parallel lines, then let's consider the equations of the line L1 being in that normal format r equals a plus lambda times the direction vector, and similarly for L2. We note that if the direction vectors c and d are the same or a multiple of one another, then we'll easily recognise that the lines are parallel. So, if this is L1, we would pick a point A on L1 and then find a vector from A to a general point P on the line L2. We know that AP needs to be perpendicular to both L1 and L2. So therefore, the scalar product of AP with both the direction vector C and the direction vector D will be 0. But if C and D are parallel and therefore multiples of each other, we'll only need one calculation. Once we know AP, we can find its length, or modulus, and this will give us the distance we want. In this example, we are asked to find the shortest distance between these parallel lines in 3 dimensions. We already know that that is going to be a perpendicular distance. We can see the direction vector of both the given lines are the same, and therefore we know that the lines L1 and L2 are indeed parallel. We can choose a point A on L1. Let's set lambda equal to 0 to do this. Then A will be 0, 1, 1. We could have chosen a different value of lambda, but we might as well make our life easy for ourselves. So, we're looking for OP. And this is going to be, given that this is the line L2 here, this is going to be 2 minus 3 mu, being the x component, minus 1 minus 4 mu, and 1 plus 5 mu. In a similar vein, AP 2 minus 3 mu minus 0, minus 1 minus 4 mu minus 1, and 1 plus 5 mu minus 1. Now we need to use that scalar product of AP dotted with the direction vector, let's call it D, equal to 0. Remembering that the scalar product is 0 for perpendicular vectors. On this slide, we've tidied up the values in AP. So, looking at the scalar product now, with that direction vector, this gives us minus 6 plus 9 mu. Remembering this is a scalar, not a vector, but I'm just writing these out because I haven't got much room. Plus 18 plus 16 mu plus 25 mu. And setting that equal to 0 would give us a value for mu of minus 1 over 25. So using mu equal to minus 1 over 25 and substituting into AP would give us the vector AP equal to 53. All of these are over 1 over 25, sorry, I'll take that out. 53 minus 46 and minus 5. And then in order to find this distance, I'm going to now look at the modulus of this, which will be equal, and I'm going to keep the 1 over 25 factor out for the moment, with the square of that 53 squared minus 46 squared and the minus 5 squared, which, if I use a calculator, would give me 15 root 22 over 25, which simplifies down to 3 root 22 over 5. So to summarise, we chose an easy point A, and then we set up the vector for P using this. So this was our point A by setting lambda equal to 0. Then we used the other line equation to set up the vector to P. We then took away A, which gave us this vector AP here. We took the scalar product with the direction vector, which was the same for both lines as they were parallel, and that gave us the value of mu. We put that in to AP and then took the modulus, which gives us the overall distance. You may have noticed that once we've chosen that first point on one of the lines, we are using the same method as in the previous video for finding a distance from a point to a line. In the next video, we will find the perpendicular distance between skew lines.